In the physical universe, the idea of nothing may only exist in theory, not in reality. Even if we remove all energy from the universe, it doesn't become truly empty. Currently, the universe seems filled with various things like matter, radiation, antimatter, neutrinos, and mysterious dark matter and dark energy.
Even if we were to take away every bit of energy, the universe would still create new forms of energy. Why does this happen? It's like the universe itself doesn't understand our idea of nothing at all. If we were to eliminate all energy, leaving only empty space, we might expect the universe to be at absolute zero with no particles. Surprisingly, that's not the case. Even if we artificially make the universe appear empty, its expansion would still produce radiation. This continues into the distant future or even back to the time before the hot Big Bang. The universe, it turns out, never truly becomes empty. With all of this, is it really possible that the universe really came from nothing? We are certain that something always exists. Even if we remove particles, antiparticles, photons, and quanta from a space, empty space still remains. If we move far from any mass or energy sources, clear the space of external electric, magnetic, and gravitational fields, and prevent photons or gravitational waves from entering, a kind of physical nothingness still exists. In this empty space, quantum fields persist. The fundamental constants and laws of physics remain. There is a zero-point energy inherent in that space with a finite, positive, and non-zero value. This seems to be the closest we can get to nothing within our universe. While you might imagine an even more nothing-like state, it doesn't have a physical reality. No experiment can create such a condition. Stick to science, and we can say that something always exists, because true nothing cannot coexist in our universe. Here in our universe today, it's very clear that space is anything but empty. In every direction we look, we see stars, gas, dust, other galaxies, galaxy clusters, quasars, cosmic rays, and even radiation both from starlight and leftover from the Big Bang itself. If we had better eyes, or let's say superior tools at our disposal, we could also detect the signals that we know ought to be out there. This includes gravitational waves from any mass accelerating through a changing gravitational field, the elusive signals from whatever makes up dark matter, and a more comprehensive view of black holes, both active and dormant, beyond those emitting the most radiation. Everything we observe happens in a universe that isn't static but is continually evolving. From a physical perspective, it's fascinating to understand how our universe is changing on a large scale. The fabric of our universe, known as spacetime, which is expanding. This means that if you place 2 points far apart in your spacetime, the proper distance between those points, the time it takes for light to travel between those points, and the wavelength of the light traveling from one point to the other all increase over time. The universe isn't just expanding, it's also cooling due to this expansion. As light stretches to longer wavelengths, it moves towards lower energies and cooler temperatures. The universe was hotter in the past and will become even colder in the future. Throughout this process, objects with mass or energy in the universe are attracted to each other, forming clusters and creating a vast cosmic web. If you could somehow eliminate it all the matter, all the radiation, every single quanta of energy, what would be left, in a way? You would have empty space itself, still expanding, still following the laws of physics, and still subject to the influence of quantum fields that pervade the universe. This represents the closest physical approximation to a true state of nothingness, yet it adheres to specific physical rules. To a physicist in this universe, removing anything else would create an unrealistic state that no longer corresponds to the cosmos we inhabit. This implies that what we currently interpret as dark energy would still exist in this hypothetical universe of nothing. In theory, if you take every quantum field in the universe and set it to its lowest energy configuration, you'd reach the zero-point energy of space. This means that no more energy can be extracted from it to perform mechanical work. In a universe with dark energy, a cosmological constant, or the zero-point energy of quantum fields, there's no reason to assume that the zero-point energy would be truly zero. As the universe keeps expanding and cooling, there will be a far-off future when radiation becomes the dominant component, surpassing other forms of matter and radiation, with only dark energy being more dominant. However, there's another period in the universe, not in the future, but in the distant past, when something else dominated besides matter and radiation. During cosmic inflation before the hot Big Bang, our universe was expanding at an incredibly rapid and constant rate. Instead of being dominated by matter and radiation, The cosmos was governed by the field energy of inflation, similar to today's dark energy but much more powerful and expanding at a much faster rate. If eternal inflation is correct, but time is still finite, where could the universe have originated? After all, there must have been a beginning, right? To tackle this question thoroughly, let's untangle three commonly confused concepts and discuss each one separately: the hot Big Bang, as it relates to our universe, the theory of cosmic or cosmological inflation, and its role in preceding and setting up the Big Bang, and the question of an ultimate beginning or origin for our universe, and why both inflation and the original idea of the Big Bang might not provide a satisfying answer to this question. In the early 20th century, a groundbreaking synthesis occurred as four crucial pieces of information, one theoretical and three observational, converged. The theoretical breakthrough by Alexander Friedmann within the framework of Einstein's general relativity demonstrated that a universe uniformly filled with any form of matter and energy cannot remain static and stable but must either expand or contract. The rate of expansion or contraction is determined by the overall energy density of space. Henrietta Leavitt's observational work established a relation between the period of brightening and fainting Cepheid variable stars and their intrinsic brightness. This is known as the period luminosity relation. Observations by Vesto Slipher measuring the shift in light, red-shifted or blue-shifted, from our solar system's frame of reference in spiral and elliptical nebulae, later identified as galaxies. These observations indicated that these galaxies were receding from us at incredibly high speeds. Edwin Hubble, along with Milton Humason, identified the same types of variable stars that Henrietta Leavitt had studied in those spiral and elliptical nebulae. This allowed them to measure the distances to these galaxies and confirm their extragalactic nature. The combination of these four pieces of information led to the formulation of the idea of the expanding universe. If the universe is expanding, it implies that as time progresses, space itself expands. Consequently, the matter within the universe becomes less dense because although matter consists of a fixed number of particles, the volume it occupies increases as space expands. Therefore, the universe becomes less dense over time. Radiation, such as photons or light waves, not only dilutes to lower densities, but as space itself stretches to greater distances. The energy of each light wave also stretches. This causes the universe not only to expand and dilute, but to cool as well. Now, if we consider what happened to matter and radiation in the universe by running the clock backward in time, precisely the opposite conditions would occur. In the past, when the universe was younger, it would have been denser and hotter.